In section 9.4, we're actually looking at how gravity affects energy. We've already seen how springs affect energy. When you do work to stretch or compress a spring, that energy is stored in the spring as elastic potential energy, and we know how to calculate that, 1/2 kx squared, where k is the spring constant. Now you'll notice that the x is squared, and that's because the harder you pull a spring, or the farther you pull a spring, the more force is required. It wasn't a constant force no matter what. The more you stretch the spring, the more force was required. So the work was actually proportional to the square of the distance, not just the distance itself, which is similar to what we see in kinetic energy. Kinetic energy, remember, is the energy of motion. The work energy theorem told us that the work done on an object is equal to its change in kinetic energy. So we had 1/2 mv squared minus 1/2 mv naught squared, where this is the term for kinetic energy, final and initial. Now you'll notice if the final kinetic energy is greater, then the work done is positive because the object gained energy. If the final kinetic energy is less, then the work done will be negative because the object lost energy. Okay? So we have that. Now we're going to go ahead and take a look at what happens when we do work with gravity or against gravity, or when gravity does work. This is going to be similar to doing work against a spring because that energy won't be gone, it'll be conserved, it'll be stored from gravity, but it's going to be a little bit different because it doesn't take any more force to lift something up 1 meter than 6 meters, because the force due to gravity is constant near the surface of Earth, because we're measuring, remember, the force due to gravity is equal to m1 m2 g over r squared, and since this distance is measured from the center of the Earth, moving something a few meters up off the surface of the Earth does not really affect the gravitational force. So what we're going to do is we're going to take a look at that activity 9.4 and see if we can make sure that all our signs are making sense all the way through. So what we have is this object, and gravity does work to slide it down this ramp this way. Now this leads us to some interesting things that go on with sine because of the force and the angle and which way they're both going, but we'll work through that. So the work done by gravity is associated Fg times d times the cosine of the angle between them. Remember, the force due to gravity is m times g. In this case, the positive x and y are here, and since g is pulling down, that is negative g, times the distance it slides, times the cosine of the angle between them. Now, since the force is down and the motion is sideways, the cosine of the angle between them is this angle theta right here, right? Because that angle is always between the force and the motion. Now, we also have this other triangle that's going to let us think about it in terms of just how high this object has gone, right? How far down did gravity pull it, as opposed to how far along the ramp. So, write an equation for the height h of the triangle in terms of theta and d. So this h over here is actually the distance down that gravity has pulled that block. And we're going to solve for d. So that is the adjacent side of this angle. So remember, that would tell us h is equal to d times the cosine of the angle theta. And if we solve that for d, we see that d is equal to h divided by the cosine of the angle. Now, we're going to take and we're going to substitute this expression for d back into this equation for the work. So the work done here is equal to negative mg times d, which we're going to replace with h over cosine of theta, times the cosine of theta. So the whole point of this was to get this messy cosine of theta to drop out, and so what we end up with is the work done is equal to negative mgh. Now, the height h can be expressed in terms of initial height and final height, which means we can actually replace this h with hf minus hi. Final minus initial gives us the change in height. And so we're going to go ahead and we're going to say, okay, so that tells us work is equal to negative mg hf minus hi, which equals mghi minus mghf. Okay? This negative distributes and it reorders the initial and final height. Now, this term, MGHI, is called gravitational potential energy. It's the energy something has because the gravitational force is acting on it. If you lift something up, you have done work against gravity, which is why this is actually the negative thing, right? If it's got a greater height, then the force and the motion were opposite of each other. That was actually causing this work. The motion was up, gravity was down, so that is why that side is negative. Now, if we go ahead and we take this equation we have for work and set it equal to the other one we have, which said 1/2 mv squared minus 1/2 mv naught squared, that's the kinetic energy, that's equal to work. Well, so is this thing with gravity, so 1/2, or not 1/2, it's just mgh, and remember this one is actually initial, so mgh naught, minus final, mgh, and no sign on that one for final. Those two things are equivalent to each other. This is the work done, this is the work done. Now, we're going to combine all the initials to one side and all the finals to the other. Since I see that my final over here is negative and my final over here is positive, I'm going to go ahead and I'm going to add this to this side, and I'm going to do the same thing and add this to this side. So what I have is 1/2 mv squared plus mgh equals 1/2 mv naught squared plus mgh naught. So my initial energy, this would be the total mechanical energy, assuming no other things are here. So my initial gravitational plus kinetic energy is equal to my final gravitational plus kinetic energy. We usually write this the other way around, so we start with our initial 1/2 mv naught squared plus mgh naught is equal to mgh plus 1/2 mv squared. Okay. And a lot of times you'll see this written instead of initial and final as 1 and 2. So if we pick any points along something's path, we can figure out what's going on with their energy. Now, this is total mechanical energy. The gravitational potential energy plus the kinetic energy. Now, if there's other kinds of energy, if there was elastic energy in there, we'd also have to account for that. So this is without friction and without any elastic potential energy. We have the mechanical energy of a system is equal to its kinetic energy, 1/2 mv squared, plus its potential energy, mgh. And this is true at any point in the system. This number is going to stay constant as long as no other forces are acting. The mechanical energy is constant. That's what it means when we say mechanical energy is conserved. So, what happens if there are other forces? What happens if there is friction? Well, we just have to deal with that by accounting for the work done by friction. Friction is always going to reduce the amount of energy in a system because what friction does is it takes mechanical energy and converts it into thermal energy. Mechanical energy is the energy due to gravity, the energy in a spring, the energy due to motion. Thermal energy is the energy of atoms, right? You increase something's thermal energy and the atoms move a little bit more. They have a little bit more kinetic energy. So it says we had an equation for the work done by gravity. We're going to go ahead and copy that down. So the work done by gravity is equal to mgh minus, or this is initial, minus mgh. Okay, so if we look at this, the net work is the work done by gravity plus the work done by friction. Okay, so we have the net work is equal to mgh naught minus mgh plus the work done by friction. Cool. Follow the same procedures in part 2, step 2 to obtain an equation that relates initial kinetic, initial potential, blah, 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 blah. Alright, so we're going to go ahead and we're going to set this mgh naught minus mgh plus the work done by friction is equal to the change in kinetic energy, 1/2 mv squared plus, minus 1/2 mv naught squared. So this is the exact same thing we did before, except this time I have this pesky work from friction in there. We're going to leave that over with the initial side. So what I end up with is the 1/2 mv squared, mv naught squared, plus mgh naught plus the work done by friction is equal to the final mgh plus 1/2 mv squared. Okay. So all we've done is we've included one more term in here. Okay, and this other term that we've added is the work from friction. Now remember, force times motion times the cosine of the angle between them is always how you calculate work. So work from friction is going to be F, the frictional force, FF, times the distance x times the cosine of the angle between them. But since friction pretty much always opposes motion, this angle is going to be 180 degrees, and the work done by friction is pretty much always going to be a negative number. And if we think about that, what that means is when we include the work done by friction, it's going to reduce this total amount of initial mechanical energy, which means at any other point later we are going to have less energy available to us, less mechanical energy. So the conservation of energy system with friction is this 1/2 mv squared, initial velocity squared, plus its initial height, mgh naught, plus the work done by friction is equal to its final height, its final gravitational potential energy, plus its final kinetic energy.